Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to try and picture something for a second. Imagine waking up on like a Saturday morning and you look out the window and it is just a genuinely grim gray day.
Oh, the worst.
Right. You know the exact kind of me. The sky is just this heavy, flat blanket of charcoal. The rain is already starting to spit against the glass.
Yeah.
And you just realize instantly that every single one of your weekend plans is completely ruined.
Just that claustrophobic, miserable feeling.
Exactly. It's miserable. But now I want you to take that exact feeling, that gray, rainy disappointment, and I want you to multiply it by infinity.
That's quite a jump.
It is. But imagine a world where it is cloudy all day, every single day. Literally no breaks in the overcast, ever.
Not a single ray of sunshine.
Right. And instead of, normal water hitting your window, there is a 100% chance of sulfuric acid showers.
Yeah, you are definitely standing on Venus.
You're on Venus, the ultimate bad weather destination.
Oh, it truly is. I mean, when we talk about Venus being cloudy, we aren't talking about, like, a passing storm front or even a harsh winter season.
Right. It's not a seasonal thing.
Not at all. We are talking about a permanent, just absolutely crushing global envelope of toxic clouds. It completely obscures the surface of the planet from space.
And it's not just the acid rain that's the problem, right?
Oh, no. If you were actually standing down there on the surface, you'd be experiencing an atmospheric pressure roughly 90 times heavier than what you feel on Earth right now.
90 times. That's just, I can't even wrap my head around that.
To put it in perspective for you, it's basically the equivalent of standing nearly a mile underwater in our oceans.
Wow.
Yeah, the environment is just so extreme, so relentlessly hostile, it almost completely defies our earthbound comprehension of what a weather system can even be.
And, the reason we're venturing into that toxic eternal gray today is because there's a massive mystery hiding inside it.
A really big one.
It's literally big. Specifically, this enormous 6,000-kilometer wide wave of clouds. And it just continuously sweeps around the equator of Venus.
It's incredible.
It's this colossal disruption in the sky that honestly baffled planetary scientists for years. But the puzzle has finally been pieced together.
It has.
And it turns out this massive atmospheric wave is actually the largest known hydraulic jump in the entire solar system.
Which is just a fascinating concept.
We are going to unravel exactly what is causing this gigantic disruption, the kitchen sink physics that actually drive it, and what it can teach us about the atmospheres of entirely different planets.
Right, because to solve a planetary scale mystery like this, researchers actually had to look at phenomena that you can recreate right in your own home.
Which is wild to think about.
It is. But before we pull apart the physics of your plumbing, we really need to set the stage on Venus.
Okay, let's do it.
Because that thick, oppressive cloud cover we just described, while it sounds like an absolute nightmare for a vacation, it is actually a dream scenario for atmospheric scientists.
Okay, wait, I have to push back on that a little bit.
Sure.
Because my first instinct when I think of a planet completely smothered in opaque clouds is that it would be an absolute nightmare to study.
Oh, I see what you mean.
Right. Like you can't see the surface, you can't see mountains or valleys from orbit to map the topography easily. Why is a permanent, impenetrable grayout actually a good thing for understanding weather?
Well, think about looking at Earth's weather from space for a moment.
Okay.
Our clouds are incredibly sparse.
Yep.
And they're intermittent. They bring apart the second they hit, the Rocky Mountains or the Himalayas.
Right. They hit a mountain and just dissipate.
Exactly. They dissipate over the vast heat sinks of the oceans. They form and vanish really rapidly based on highly localized humidity and temperature changes.
So it's messy.
It's very messy. It's a chaotic, disjointed system that is heavily influenced by the jagged surface below it.
Ah, okay.
But on Venus, that constant thick cloud cover gives us a continuous, uninterrupted laboratory for fluid dynamics.
Because there's nothing in the way.
Yeah. Right. The atmosphere acts like a unified, cohesive fluid envelope. It's entirely separated from the ground level.
Oh, that makes a lot of sense when you put it like that.
Yeah, it allows us to observe massive flow processes that would just be completely masked or broken up by the patchy topographical interference here on Earth.
It's sort of like it's the difference between tracing a current in a muddy, rocky stream where the water keeps hitting obstacles versus tracing a current in this massive, deep, unobstructed river.
That is a perfect analogy.
Yes. The sheer volume and continuity of the medium actually highlight the overarching movements within it.
Exactly.
And those overarching movements are exactly what Japan's Akatsuki Venus orbiter was hunting for.
And, the Akatsuki probe's mission is just an incredible story of persistence on its own.
It really is.
It became an absolute game changer for our understanding of this alien atmosphere. The probe actually missed its initial orbital insertion around Venus back in 2010.
Because of an engine failure, right?
Yeah, main engine failure. So it basically just drifted around the sun for 5 whole years.
That's agonizing.
Oh, I can't even imagine being on that engineering team. But they brilliantly managed to use its smaller attitude control thrusters to coax it into a highly elliptical orbit in 2015.
Talk about a comeback.
Right. And when it finally started gathering data in 2016, it was utilizing a suite of really specialized cameras, particularly its near-infrared cameras.
And why near-infrared specifically?
Well, visible light, the kind our human eyes process, it just bounces right off the highly reflective upper cloud deck of Venus.
Which is why the planet looks like a bright, featureless pearl in our night sky.
Exactly. But near-infrared wavelengths can actually pierce deeper. They penetrate those blinding upper layers to reveal the thermal dynamics of the denser, lower, and middle cloud regions.
And when they pointed those near-infrared cameras into that haze, the images they captured were just jaw-dropping.
Completely unexpected.
They saw this clear, incredibly dense, darkly dark line of clouds moving across the planet.
Yeah.
And the scale of this structure is just staggering. It was measured at 6,000 kilometers wide.
It's massive.
Just to help you visualize that, 6,000 kilometers is roughly the distance from New York City all the way across the Atlantic Ocean to Paris.
It's a continent-sized structure.
Right. Imagine a single, cohesive, uninterrupted weather front stretching from the Statue of Liberty to the Eiffel Tower, sweeping across the globe for days at a time.
A weather structure of that magnitude is almost impossible to comprehend through an Earth-centric lens.
Truly.
And it wasn't just, a fleeting anomaly either. This colossal wavefront would repeatedly sweep around the planet's equator. It maintained its structure and its organization in an environment that is otherwise violently turbulent.
Okay, let's unpack this for a second. If the entire planet is just a uniform blanket of thick clouds 24/7, I'm struggling with how we even distinguish a wave in the first place.
Right. How do you see it?
Yeah. If I'm looking at a dense fog bank, another patch of fog doesn't really stand out. How does a cloud make itself known against a background of literally nothing but other clouds?
It really comes down to understanding what the near-infrared camera is actually showing us. Okay. It's not taking a photograph of a cloud in the traditional sense. It's mapping thermal radiation.
Mapping heat.
Right. The lower atmosphere of Venus is intensely hot, and that heat naturally radiates outward into space.
Right, heat rises.
Exactly. The near-infrared cameras pick up that glowing heat as a bright background.
Got it.
So when we see the wave, it doesn't look like a fluffy white Earth cloud against a blue sky. It appears in a very distinct dark streak against the brighter background of the surrounding thermal radiation.
So the dark streak means something is blocking the heat from escaping?
Yes.
The clouds in that specific wavefront must be much denser, acting like an insulating blanket.
They are significantly denser, and crucially, they're being pushed higher up into the atmosphere.
Which means they're colder.
Exactly, which means they're cooler. So you have a massive organized wall of denser, cooler material bulldozing its way through the relatively more uniform background clouds, and it's blocking the thermal glow from below.
Man, so it's not just a ripple on the surface. It's a solid, continental-sized wall of material forcing its way through the sky.
That's exactly what it is.
And when scientists like Professor Takeshi Imamura from the University of Tokyo first identified this phenomenon in the Akatsuki data back in 2016, they knew immediately they had found something profound.
Oh, absolutely.
Because you don't get a highly organized 6,000-kilometer wide structure in an atmosphere by pure chance.
No, physics is at play there.
Right. But identifying it was only the first hurdle. Because for years, they simply couldn't understand its origin. It completely defied all the established models for how the Venusian atmosphere was supposed to behave.
Because to understand how a structure that massive can even form, let alone maintain itself, We have to talk about the absolutely bizarre environment it's traveling through.
The atmosphere itself.
Right. We aren't looking at a static atmosphere hanging over a rock.
Right.
We're looking at a planetary envelope that is completely decoupled from the ground beneath it.
Decoupled. Okay.
We have to look at the phenomenon of superrotation.
Oh, superrotation is one of those concepts that just forces you to completely rewire how you think about planetary physics.
It really messes with your intuition.
It does, because the clouds on Venus move about 60 times faster than the planet itself turns.
Yeah.
If you stood on the surface of Venus, the ground is barely moving, but the sky above you is screaming past at hundreds of kilometers an hour.
See, on Earth, our atmosphere generally rotates along with the solid mass of the planet.
Right, they spin together.
We have trade winds and jet streams, sure, but the air mass as a whole turns with the globe. Venus, on the other hand, is an incredibly sluggish world.
Very slow.
A single day on Venus, meaning one full rotation on its axis, takes about 243 Earth days.
That's so weird to think about.
It actually takes longer for Venus to spin around once than it does for it to orbit the sun.
So the planet itself is basically taking a leisurely, agonizingly slow stroll through space.
Yet its atmosphere, that massive crushing envelope of sulfuric acid clouds, races around the entire planet in just 4 Earth days.
4 days.
It is whipping around the equator at breakneck speeds.
It's like, imagine standing on a treadmill that is turned off, completely stationary, but the air conditioning in the gym is blowing past your face at hurricane speeds in a constant, never-ending circle.
That's a great visual.
That is the engine of superrotation. And from what I understand, we actually see this phenomenon elsewhere in the universe. It's not just an isolated cosmic freak show.
No, not at all. Superrotation is actually a fundamental fluid dynamic behavior under very specific planetary conditions.
Where else do we see it?
Well, we see it on Titan, Saturn's largest moon. We see a variation of it on our own sun, where the plasma at the equator rotates significantly faster than the plasma at the poles.
Oh, fascinating.
We even see a highly localized form of superrotation in Earth's uppermost atmospheric layers. But on Venus, it is the defining dominant characteristic of the entire global weather system.
But here's where I get stuck.
Yeah.
If the planet is barely spinning, what is the engine driving these clouds at 60 times the speed?
It's a great question.
Because you have this massive, sluggish ball of rock. Where is the energy coming from to keep the air screaming around it? My first thought is like a chicken and egg scenario.
Right.
Is this giant 6,000-kilometer wave we just talked about causing the superrotation, or is the superrotation causing the wave?
You are hitting on the exact paradox that scientists wrestled with for decades.
Oh, really?
Yeah. The primary engine for superrotation is actually the sun.
The sun. Just the heat from it.
Exactly. Venus receives a tremendous amount of solar radiation. And because the planet spins so slowly, the side facing the sun gets incredibly hot, while the dark side cools down.
So there's a huge temperature difference.
A massive temperature differential. And this creates what we call thermal tides, basically huge waves of heating that push the atmosphere around.
Okay, I'm with you.
But thermal tides alone aren't enough to maintain speeds 60 times faster than the planet. They need a mechanism to transport and maintain that momentum.
So the heat gets the air moving, but there has to be something keeping it moving, stopping friction from just slowing it all back down to a crawl.
That is exactly where the wave comes in. The relationship is entirely symbiotic. The extreme speed of the superrotating atmosphere provides the fast-moving fluid medium necessary for these massive waves to form.
Right.
But the mathematical models show that the energy and momentum transported by the specific, newly discovered wave process actually flow back into the system to help maintain the superrotation itself.
So they feed each other.
Yes. The wave isn't just a passenger riding the fast winds. It is a vital gear in the engine, helping to transfer momentum and keep that atmospheric envelope spinning wildly out of sync with the planet.
So the sun heats the atmosphere and gets it moving. The fast-moving atmosphere creates these massive waves, and the waves in turn transfer momentum to keep the atmosphere spinning.
You got it.
It's a gigantic planetary feedback loop. But, that still leaves the core mystery completely unanswered.
It does.
We have a fast-moving atmosphere. We have a giant dark streak of dense clouds. But what is the physical trigger creating that specific 6,000-kilometer wall?
Right.
If it's a wave, What is the rock that got dropped in the pond to make the splash?
Well, to find that rock, we have to step away from the massive scale of planetary orbits and supercomputers and thermal tides for a moment.
Okay.
We need to look at a very specific, fairly mundane piece of physics. We need to look at what happens every time you turn on your kitchen sink.
I love this so much. We are taking a toxic, alien weather system that encompasses a whole planet and explaining it with dishwashing.
It's the best way to understand it.
So what is this secret mechanism?
The secret mechanism, the solution to this years-long mystery, is that the massive cloud wave on Venus is caused by the largest known hydraulic jump in the solar system.
A hydraulic jump.
Sure.
Let's break down exactly what that is.
Sure.
In fluid dynamics, a hydraulic jump is a phenomenon where a fluid abruptly slows down, right? Changing from a shallow, very fast-moving state to a deep, much slower-moving state.
Exactly. And the kitchen sink analogy is really the most intuitive way to visualize this.
Walk me through it.
Imagine you walk over to your sink, the basin is flat and empty, and you turn the tap on full blast.
Okay.
The water streams straight down and strikes the bottom of the sink.
And when it hits, it spreads outward in a perfectly smooth, very thin, incredibly fast-moving circle.
Right.
It almost looks like a disc of clear glass pressed against the bottom of the basin.
Yeah, that smooth, fast-moving water is in what fluid dynamicists call a supercritical state.
Supercritical.
The velocity of the fluid is actually moving faster than the speed at which waves can travel through that fluid.
Wait, really?
Yes, it's moving so fast that if you dropped a pebble into that clear disc, the ripples couldn't travel backward against the flow.
Oh, wow. I've never thought about it like that.
But as that water spreads outward from the center, friction from the bottom of the sink and the expanding surface area cause it to lose kinetic energy.
So it inevitably has to slow down. And it doesn't just gradually, smoothly slow down until it stops. It suddenly hits a boundary.
Yes.
There is a distinct ring around that smooth circle of water where it suddenly ripples, becomes turbulent, and pools up much deeper.
Right.
You can clearly see the distinct edge where the water literally jumps up in height. That ring of turbulent, deeper water surrounding the smooth, fast water, that is the hydraulic jump.
You've got it. The fluid abruptly transitions from supercritical to subcritical flow, from fast and shallow to slow and deep.
Right.
And the conservation of energy demands that the excess kinetic energy of the fast water has to go somewhere when it slams on the brakes.
It can't just disappear.
Exactly. Some is lost to heat and sound, but the bulk of it is converted into potential energy, specifically by raising the height of the fluid. The water is forced upward.
Okay, so if the Venusian atmosphere is the kitchen sink in this scenario, what exactly is acting as the water tap?
Good question.
Because we are talking about vast rivers of atmospheric gases moving horizontally here, not a physical stream of water pouring downward out of a faucet onto a flat basin. Where is the fast-moving fluid originating?
We have to map the mechanics of the sink onto the grand scale of the Venusian atmosphere.
Okay.
On Venus, the fast-moving fluid isn't pouring downward from a source. Instead, the high-velocity flow is provided by a naturally occurring atmospheric phenomenon called a Kelvin wave.
A Kelvin wave.
Yeah.
I've heard of those in relation to Earth's oceans, right? Particularly with El Niño events, where massive waves of warm water travel across the Pacific along the equator.
Yes. The physical principles are incredibly similar. Kelvin waves are massive, naturally occurring waves that are trapped at the equator by a combination of planetary rotation, and even Venus's slow rotation plays a part here, and atmospheric boundaries.
Okay.
Because of the incredible speed of the atmospheric superrotation we discussed earlier, these Kelvin waves on Venus are carrying vast amounts of atmospheric gas eastward at extraordinarily high velocities.
Right through the lower and middle cloud regions.
Exactly. They are colossal horizontal flows of gas, acting identically to that fast, shallow, supercritical water spreading across the bottom of your sink.
So we have this massive, invisible river of gas racing eastward around the planet's equator. It's moving incredibly fast, mimicking the smooth, glass-like water in the sink.
Right.
But for a hydraulic jump to occur, something has to force that flow to slam on the brakes, just like the water hitting the frictional boundary layer in the basin.
Yes. The eastward-moving Kelvin wave eventually becomes unstable.
Unstable how?
Well, the precise causes of this instability are complex. They're heavily tied to the intense temperature gradients between the lower atmosphere and the cloud layers, as well as structural shifts in atmospheric density.
So it hits a rough patch, essentially.
Basically. But the result of this instability is instantaneous and incredibly dramatic. The wind speed, as seen from the perspective of the traveling atmospheric wave, abruptly and violently decelerates.
And when a massive volume of fluid suddenly decelerates, that forward momentum has to be displaced. Like you said, it can't just vanish. In the sink, the water jumps upward and gets deeper. In the atmosphere of Venus, this sudden breaking of the Kelvin wave creates a massive, localized vertical updraft.
It pushes straight up.
But I'm trying to picture this physically. If I imagine a crowd of thousands of people sprinting down a wide street and the front row suddenly stops, the people behind them don't fly up into the air.
Thankfully, no.
They just crash into each other and spread outward into the alleys. Why doesn't the Venusian gas just disperse sideways or backwards when it slows down? Why is the force so intensely vertical?
It comes down to the immense pressures and the rigid stratification of the Venusian atmosphere.
Okay.
Venus has 3 distinct, highly pressurized cloud layers, and they act almost like physical ceilings and floors.
Oh, I see.
When the fast-moving gas in the lower and middle layers hits this point of instability and decelerates, it is trapped.
It has nowhere to go.
Exactly. It has the immense crushing pressure of the deep atmosphere below it, and it has the horizontal flow piling up behind it like a snowplow pushing into a massive drift. The numerical simulations of this event show what is called a stepwise transition of the material surface.
A stepwise transition, meaning the atmospheric layer actually takes the shape of a literal staircase or a sharp cliff edge.
Yes. The horizontal momentum is so vast and the deceleration is so violent that the path of least resistance for the fluid is to erupt straight vertically.
Straight up.
As Professor Imamura pointed out, this dynamic was highly unexpected.
Why is that?
Well, in planetary fluid dynamics, you typically have massive horizontal processes like jet streams or planetary waves, and you have entirely separate localized vertical processes like a thunderstorm updraft driven by surface heat.
Right, they don't usually mix like that.
Exactly. Connecting a planetary scale horizontal wave directly to a powerful localized vertical geyser of gas is incredibly rare. The horizontal crash directly fuels the vertical updraft.
And it's not just invisible air that is being violently shoved upward either.
No, definitely not.
The lower cloud layers of Venus are incredibly hot. They hover around temperatures where lead would melt, and they're saturated with sulfuric acid vapor.
Yep.
So this updraft is carrying massive amounts of that toxic vapor higher into the atmosphere.
Which brings us directly back to what the Akatsuki probe actually saw.
The dark line.
Yes. This forced updraft acts as a planetary scale elevator for the sulfuric acid vapor.
Okay.
Deep down in the lower atmosphere, the temperatures and pressures are so high that the sulfuric acid remains in a vapor state.
Invisible.
Right. But as this localized updraft forcefully thrusts that vapor higher and higher into the upper atmosphere, it encounters a drastically different environment. The temperature begins to plummet.
And if you take a hot, saturated vapor and violently push it into a freezing environment, it condenses.
Exactly.
It's the exact same physics as stepping out your front door on a freezing winter morning and breathing out. Your warm, invisible breath suddenly hits the cold air and condenses into a highly visible cloud of droplets.
That's spot on. The sulfuric acid vapor cools rapidly as it is pushed to higher altitudes by the sheer force of the hydraulic jump.
Oh.
It condenses out of its vapor state into thick, heavy liquid droplets. And these droplets instantly form a massive, dense line of trailing clouds directly above the point where the horizontal wave originally slammed on the brakes.
And because these newly condensed clouds are significantly thicker, denser, and higher up than the surrounding weather, they perfectly block the thermal radiation glowing from the hot surface below.
Yes.
Which is exactly why they appear as a stark black streak to the near-infrared cameras.
We are literally seeing the crest of the hydraulic jump.
That is so cool.
We are looking at the foaming, turbulent ring of water from your kitchen sink translated into a planet-spanning 6,000-kilometer-wide wall of condensed sulfuric acid.
It's amazing. We started with a mysterious dark streak on a photograph, and we've drilled all the way down to a planetary-scale snowplow effect driven by the physics of dishwashing.
Science is wild like that.
But proving this mechanism, that's a completely different mountain to climb.
Wow, absolutely.
Because you can't just fly a weather balloon into a Venusian wave to check the wind speed and the Froude number of the fluid flow.
I wish we could, but no.
They had to model it computationally and simulated the complexities of an alien world has to be an absolute nightmare for a computer.
It is arguably one of the most demanding computational tasks in modern planetary science.
I believe it.
The researchers couldn't rely on basic observation to prove the hydraulic jump theory. They had to recreate the physics mathematically from the ground up.
How do you even start doing that?
Well, to do this, they used a combination of highly sophisticated models, specifically pairing a fluid dynamic model with a microphysical box model.
Okay, let's break those two things down, starting with the fluid dynamic model.
Sure.
I imagine this is essentially a massive numerical analysis that simulates how the gases flow and interact, right? Plugging in the pressures, the blistering temperatures, and the 60 times faster superrotation of Venus.
Exactly. The fluid dynamic model handles the macro-scale physics. It calculates the massive horizontal movement of the Kelvin waves, the friction, the thermal heating from the sun, and the exact atmospheric conditions necessary to trigger the instability.
Okay, that makes sense.
But a fluid model alone just gives you wind speeds and pressures. It doesn't show you the clouds.
Oh.
That is why they had to pair it with a microphysical box model.
And what does that do?
This is an incredibly elegant mathematical approach where you isolate a small theoretical box or section of air and track its specific internal behavior as it is moved through the larger fluid dynamic simulation.
So you are tracking the chemistry inside the box.
Yeah.
You monitor how the pressure changes as it gets shoved upward, how rapidly the temperature drops, and the exact moment the sulfuric acid vapor nucleates and condenses into a liquid droplet.
Exactly. The fluid dynamic model provides the wind and the violent vertical updraft. And the microphysical box model rides that updraft to show exactly how, when, and where the invisible vapor turns into the dense cloud we see. They had to mathematically marry the macro movement of an entire planet with the microchemistry of a single condensing droplet.
And when they ran this paired simulation, it produced the exact same cloud disturbance. The identical dense dark line that the Akatsuki probe observed in reality.
Perfectly matched.
The math perfectly matched the photograph, proving the hydraulic jump was the engine.
Oh.
But this brings up a massive question for me.
What's that?
We have incredibly powerful supercomputers. We have standard models for weather that we use every day. Why was this such a surprise? Why can't we just plug this new hydraulic jump discovery into the existing global climate models we already use for Venus? Why did the old models miss it completely?
This exposes a really critical limitation in our current climate modeling technology.
Right.
Up until this discovery, scientists relied heavily on standard global circulation models, or GCMs, to understand planetary climates.
GCMs.
Right. We use GCMs for Earth, Mars, and Venus. The way a GCM works is by dividing the planet's entire atmosphere into a three-dimensional grid.
Like a mesh.
Yes. The computer then calculates the physical processes, temperature, wind speed, pressure within each individual grid cell to simulate the overall global climate.
Oh, I see. It's like if I'm playing an open-world video game. The computer doesn't render the entire world perfectly all at once. It renders the terrain in chunks.
Exactly.
The GCM wraps the planet in a giant digital quilt, and every square patch of that quilt is constantly calculating its own local weather and passing that data to the next patch.
That is a perfect analogy. But here is the critical flaw regarding the Venusian wave. Traditional GCMs completely miss the hydraulic jump because of grid resolution.
The squares were too big.
You guessed it. To simulate an entire global climate without taking a decade to process the data, the grid cells in a GCM have to be relatively large. You are looking at blocks of atmosphere that might be hundreds of kilometers wide.
And while a hydraulic jump is massive in its length spanning 6,000 kilometers across the equator, the actual mechanism, the sudden braking and the violent vertical updraft, is incredibly localized.
It's very narrow.
Right, it happens abruptly in a very specific, narrow band of atmospheric transition.
So because the GCM grid squares were so large, the model essentially stepped over the jump.
It just smoothed it out.
Exactly. The sudden, sharp cliff of the vertical updraft got smoothed out by the math, averaging out the conditions over a massive area. The resolution was simply too low to notice the violent microphysics happening at the boundary layer.
Well, if we know the resolution is the problem, why not just make the grid square smaller?
Yeah.
Make a higher resolution model.
I mean, if you want a global model that accurately reflects the macro-scale superrotation sweeping across the entire planet,
Right.
but you also shrink the grid cells down enough to have the microscale resolution required to accurately calculate the abrupt vertical leap of a hydraulic jump, the amount of data points the computer has to process grows exponentially.
Oh, man. Returning to the video game analogy, it's like asking a computer to render an entire sprawling, continent-sized open world, but requiring it to simultaneously calculate the individual aerodynamics and shadows of every single blade of grass bending in the wind in real time.
Yes.
The processing unit just chokes and crashes.
It absolutely does. Even with the most advanced modern supercomputers in the world, running a simulation that seamlessly connects planetary-scale horizontal waves with highly localized, high-resolution vertical microphysics is an immense computational bottleneck.
It's just too much math.
It is. But finding a way to meet that challenge is absolutely essential, because the implications of this discovery do not stop at the upper clouds of Venus.
Right, because the moment you realize this is driven by universal fluid dynamics, it echoes out across the rest of the solar system.
That changes everything.
Well, this is the very first time humanity has ever observed a hydraulic jump of this incredible scale on another planet. The underlying physics driving it are not unique to Venus. The math of the kitchen sink works everywhere in the universe.
That is the profound beauty of fundamental physics. Professor Imamura and his team have explicitly pointed out that under the right atmospheric circumstances, other celestial bodies could absolutely host massive hydraulic jumps.
And the prime candidate for this is Mars, isn't it?
It is Mars.
Now that seems counterintuitive at first glance, because Mars has a completely different atmosphere than Venus.
Vastly different.
It's incredibly thin, mostly composed of carbon dioxide, and it's freezing cold. The surface pressure on Mars is less than 1% of Earth's, whereas Venus is 90 times heavier.
Right.
How could the exact same violent hydraulic jump happen in an atmosphere that is barely thicker than a vacuum?
Because the fundamental physics of a hydraulic jump are not dependent on the type of gas or the chemistry or even the overall density of the atmosphere.
Oh, really?
They are entirely dependent on the dynamics of the fluid flow. The critical ingredients remain exactly the same. You need a fast-moving, shallow flow of fluid, and you need it to suddenly hit a boundary or an instability that forces it to rapidly decelerate and transition into a slower, deeper state.
But does Mars have atmospheric waves moving fast enough to actually trigger that?
It absolutely does. We see localized superrotation and incredibly fast jet streams in the upper Martian atmosphere.
I didn't know that.
Yeah, and Mars also has massive, jagged topographical features, like Olympus Mons, the largest volcano in the solar system, and massive canyon systems.
Which act like the bottom of the sink.
Yes, they act as brutal physical boundaries to atmospheric flow. If a high-velocity Martian wind hits the right thermal instability or topographical barrier and abruptly slows down, the physics demand that a vertical hydraulic jump will occur.
So the density of the gas only dictates the force, not the mechanism.
Not exactly.
And this highlights why building these insanely complex, computer-breaking models is so critically important.
It really is.
It isn't just an academic exercise to satisfy our curiosity about a mystery on a toxic planet we can't even stand on. It is about building a universal, foolproof, mathematically sound understanding of planetary atmospheres.
Consider the practical application for a moment.
Yeah.
We are actively planning future exploratory missions to Mars.
Right.
Whether we are sending delicate, multi-billion-dollar robotic landers, complex drone helicopters like Ingenuity, or eventually human beings, we absolutely must understand these extreme fluid dynamics.
Because if we send a descent vehicle hurtling into the Martian atmosphere, relying on a global climate model that completely missed massive localized vertical updrafts simply because our grid resolution was too low, that vehicle could encounter unexpected, violently localized turbulence.
It could jeopardize the entire mission.
Wow.
A hydraulic jump creates an incredibly turbulent shear zone. If a lander hits a sudden, unmapped vertical geyser of air while trying to execute a precision landing, the aerodynamic stress could be catastrophic.
It could just rip it apart.
It could. Incorporating the mechanisms of this Venusian hydraulic jump into our broader planetary models is a massive, necessary step forward in ensuring the safety and success of future space exploration.
It teaches us that we can no longer afford to look at horizontal winds and vertical updrafts as completely separate systems.
No, we have to look for the sudden, violent collisions between them, no matter what planet we are orbiting.
We have to map out the atmospheric bottlenecks before we try to fly through them.
Precisely.
So to just sort of retrace the incredible journey we went on today, we started by looking at a mysterious, dark streak stretching 6,000 kilometers across the toxic, unbroken, claustrophobic gray sky of Venus.
A huge mystery.
It was a puzzle that baffled planetary scientists for years. because it defied everything our models said should be happening.
But by looking closer.
Right, by looking closer with the near-infrared cameras of the Akatsuki probe piercing through the blinding upper clouds.
Yep.
And by trusting the fundamental everyday physics of fluid dynamics, we found the answer hiding in the mechanics of a literal kitchen sink.
We discovered that massive, fast-moving horizontal rivers of gas, the Kelvin waves driving the planet's superrotation, were suddenly hitting an instability and slamming on the brakes.
And this created the largest hydraulic jump ever observed.
This violent deceleration had nowhere to go but up, forcing a massive, planetary-scale vertical updraft.
It violently shoved sulfuric acid vapor higher into the freezing upper atmosphere, where it condensed into the colossal, dark, heat-blocking cloud wall that sweeps across the Venusian equator.
And in solving this mystery, we didn't just learn about the bizarre mechanics of Venus. We learned about the critical flaws in our own computer models, and we discovered how to build better, more accurate simulations for the weather on Mars and worlds far beyond our own neighborhood.
It is the perfect example of how studying the absolute extremes of our solar system brings our understanding of universal fundamental physics into much sharper focus.
It really is.
It really is. And it leaves me with one final lingering thought for you all. Yeah. If a mundane, everyday quirk of fluid dynamics, the exact same physical mechanism that happens every single time you turn on the tap to wash your dinner dishes, can drive 6,000-kilometer atmospheric waves, force vertical geysers of toxic acid, and help superrotate an entire planetary atmosphere.
It makes you wonder.
It really does. What other hidden, everyday physics phenomena are secretly acting as the engines for the wildest, most violent weather systems on the undiscovered exoplanets out there?
That is a great question.
If the plumbing of a kitchen sink can explain Venus, what other household secrets are waiting to be found in the deep cosmos?
I love that.
It's definitely something to think about the next time you're standing at the sink watching the water pool up. Thank you so much for joining us for this conversation today. Keep looking up, and we will catch you next time.